All right, looks like we're going live.
And we are.
Yep.
I'm still waiting for Kevin though.
We are. There we go. Kevin's just arrived. I'm admitting him.
Hello there.
Hi, Kevin. How are you?
Good. Sorry for cutting that close.
That's all right. Kevin, let me go ahead and make you a co-host.
Great.
Hey, Kevin, can you say your last name for me?
Van den Wymelenberg.
Wymelenberg. Okay.
Yeah.
I'm pretty sure I'm the first guy to ask you that though, right?
Yeah. No, it's all good. If you trip on it, I always make a joke. So no worries.
We already have 6 people watching, so that's good news.
Straight for the YouTube channel.
Yeah.
All right. We're about 2 minutes away from starting. Let me. Okay. Kevin, are you able to share your screen?
Yep. There we go.
All right. Looks good. We'll start in 1 minute. Okay. Damien, can you go ahead and admit people from the waiting room? Hi, my name is Nathaniel Jones, and I'd like to thank you for joining this webinar, A Delicate Balance, Energy Efficiency and Indoor Air Quality in the COVID-19 Era by Kevin Vanden Weimelenberg. This webinar is hosted by the IBPSA-USA Research Committee with the goal to share new ideas from research to the building simulation community. If you have questions during this webinar, please type them into the chat window. At the end of this 40-minute presentation, I will unmute you for a discussion with Kevin. AIA Continuing Education Credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. And now I'd like to turn it over to Kevin Vanden Weimelenberg.
All right, thank you, Nathaniel. Hello, everybody. Thanks for the invitation to be here. It's a beautiful sunny day in Eugene, Oregon, and I'm gonna get my circadian dose here by letting the sun hit me in the face. I know there is the continuing education slide. Nathaniel, did we need to say anything more about this? I can't remember, I'm sorry.
Just want to remind everyone to email info@aiaeb.org to receive credit for the course.
There we go. Thank you. I knew that I was missing something. All right, so goal for the day is to share a little bit about our research on healthy buildings, but specifically on COVID and pathogen related aspects of creating and supporting healthy buildings. I'm going to back up a little bit from it and say we've been doing microbiome.
Damien, can you go ahead and admit people from?
We'll back up a little bit and talk about the microbiome research that we had been doing before COVID, started to create problems in our buildings. Then we'll talk through some of the COVID related research, move toward mitigation and layered risk reduction strategies, try to talk about ways we can quantify both the mitigation strategies as well as their effectiveness. And finally, a little bit about simulation and how simulation may find a foothold in where we're heading in a COVID era future. I had one virologist from the UK that I was speaking with, and on another call related with one of the medical docs from the Pfizer vaccine team. And we talked about the year 2020 as the year of COVID, and he sort of chuckled and said, no, the 2020s will be the decade of COVID and likely beyond that. So I think the notion that we're going to be living with another substantial infectious disease that finds transmission pathways in our buildings is here to stay. So let's design for it. Let's figure it out. Let's find ways to design and occupy spaces that are healthy and energy efficient. So that's the goal for today. Quick background. I have to add this disclosure slide. It's a requirement of the university. At the bottom there, it talks about transparency. So I am a university professor full-time. That's my job. That's what I do. But in the pandemic era, there were some interesting risk limitation strategies that my university asked me to consider. And some of that meant I ended up starting to do some work privately, mostly because the structure of the university isn't super conducive to doing work that has larger liability profiles. And so any of the COVID related consulting work I do is through a private company called Ductal. And then any of the viral environmental surveillance work I do that is not research is run through a company that I provide a scientific advisory role for called EnviroTech. So those are the disclaimers and a little bit about why. The Institute for Health in the Built Environment, this is a slide to just try to give you the context of who we are and how we work. So it's a multi-university partnership. I don't like to call it an umbrella, maybe more of a crucible or some sort of connective tissue between people with like-minded interests. and really a diverse range of capabilities and expertise. I'll say no single university's got the range of expertise needed to handle this healthy building problem. Really what we need is to collaborate. And no college has the diversity of experience needed to really attack and solve these really challenging healthy building problems from a single discipline. We need multiple disciplines. And so you can see there at the top left, there's a lot of universities that we're fortunate enough to collaborate with, and a diverse range of expertise from public health to the OBGYN team to the School of Medicine to schools of engineering and chemical engineering and computer science, data science, So that's the kind of constellation of capabilities that we're trying to knit together. And then I think it's important to recognize that industry is really critical to work together with folks on the ground, especially when you're talking about architecture and buildings, work together with folks that are building buildings and operating buildings. So whether those are large corporations that have, multinational footprints in terms of structures like Nike and Microsoft, or manufacturers of specific technologies that might support healthy buildings like Siemens and Velux, or design professionals that are specifying and conceiving and implementing these design ideas, all are important. And so this industry connection is a formalized structure and relationship where those industry partners pay like a subscription fee. And then together we conceive of research problems that we work on. And my argument is that by connecting with industry in this way, we're asking better questions as researchers. And by solving the problems together with industry, we're being more innovative. It's a give and take, and then ultimately, if that all works, the practice gets better faster, and these ideas don't sit on shelves collecting dust in white papers. They manifest themselves in the real world. So that's the vision. All right, the unseen in the built environment. We're made of trillions of microbes. Our gut microbes regulate our digestion and impact our mood, our weight. Our skin microbes have immunoprotective effects. By mass, we're about 5 kilograms non-human microbial life. By cell count, we're more non-human than we are human. Humans comprise 70 trillion cells. We eat about 20 billion bacterial cells every day. We inhale about 3 billion. We drink about 40 million. And that's in privileged, purified drinking water perspectives. Everything from our skin to our gut to the Mars rover is covered with diverse microbial ecosystems, and really there's no getting away from it. Understanding the indoor microbiomes opens an opportunity to better understand human health and look for this relationship between humans and microbes and the petri dish that we call buildings. And this was true before COVID, and it's even more viscerally understood now in this COVID era. I hesitate to call it post-COVID because we're not there yet, and I don't know how soon we will be. Okay, so that's some visualizations that we put together about a decade ago, trying to understand how buildings and microbes work together. And since then, we've done a lot of more foundational research to understand what's the microbial community structure in our buildings. What do we do as designers that implicate that microbial structure? What do we do as engineers and building operators that shift and shape the bacterial or overall fungal, bacterial, viral community structure? What can we do to modify it? What can we do to intervene either in design stages or in building operations? What are the role of some really key fundamental aspects of building operations, building design, and sustainable building strategies, like the choice of materials, the access to fresh air from natural ventilation or filtration and heat recovery? What about the role of light and daylight? What about UVC? All of these things. And so we've taken a lot of independent and discrete studies, and then we're trying to aggregate them to better understand, how do you create a healthy building microbiome? And the first and most obvious it's easy to say we want to get rid of the bad microbes, we want to get rid of the bad actors. I think what's more challenging is to understand, how do you cultivate a garden of healthy microbes that are supportive of health? I'm seeing the chat window, and I'm just going to ignore the chat window unless, Nathaniel, you interrupt me and say, hey, somebody has a really burning question and it's relevant right now, answer it. So, okay, so we have 2 polls that I thought we'd start off just to get a little extra engagement. Here's the first poll, and hopefully we can figure out, make it work in Zoom and everything, and we'll present the results here in a minute. But I wanted to get a sense for where we're at. Look, we're a year into this pandemic. I'm talking to you from my spare bedroom, which is no longer a spare bedroom. We haven't had house guests in forever, and it's been my office for the better part of the last year. And I just want to see how many of us in this group, probably largely an office work kind of group. Maybe some of you spend a fair amount of time, with rolls of blue tape and hard hats, I don't know, in buildings. But I just want to kind of get a sense for where we're at right now. Where are we working from these days? All right. So the poll results, I'm not sure how I share them, but I can just recite them if nobody is seeing them. 76% of us are working from home. 12% of us are working from home most of the time, more than 75% of the time. And 6% of us are working from home less than 50% of the time. And only 6% of us are basically working in the office right now. That's striking, right? Because probably every single organization that you work for, that we are all working for, is paying for commercial real estate, office space somewhere that is largely sitting underutilized. And this is definitely starting to rock the commercial real estate and real estate investment trust communities. They're seeing leases not be renewed. They're seeing leases being downsized. And it's fundamentally changing our urban centers. Cities look like ghost towns. And I think nobody could have predicted that we could make work continue this way. It's probably working better than most people thought, but I will also argue, a year in, I'll just speak for myself, I'm sick of it. I don't want to keep working this way forever. I think maybe a little bit of more flexibility is here to stay. But getting back into offices is pretty critical. But before I go too much further in my rant there, we'll launch the second poll, and then I'll just continue. Where do we think we're going to be in 6 months? If this is the normal for the last 12, where will we be in 6 months? Well, how optimistic are we that this is going to fundamentally change? Or do we think we'll just be where we're at? All right, we're getting close. Get your votes in. All right, I think we're pretty close to people who are going to vote have voted. So we have more optimism. We have optimism going forward. Maybe based upon, like, I'm sick of this, or based upon 6 months from now it's going to be June, so life will be better in June, or based upon the vaccine and our anticipation for the vaccine rollout, or some combination thereof. So only 26% of the people predict that we'll be 100% from home. 23%, so roughly half, say we're still going to be working mostly from home, 75% or more of the time. But 29% of people say, 50 to 75% of the time from home. So on the balance, I'd say we're slightly more optimistic, but really only 23% of the people say we're going to be at home less than half the time. So I think it goes to suggest that we're probably living with this hybrid environment for a while, and we probably need to think pretty aggressively about what it's going to take to change so that we can live in buildings again. We wrote this paper originally in late February and then in early March, and actually it had 5 or 6 different versions of the paper between updates to preprints and then a publication and an update to the publication. And we finally have just stopped trying to update it because things just keep changing so fast. But so it's got, it represents a snapshot in time, roughly the February, March, early April, early pandemic in the USA perspective. It was originally written with, hey, if you're thinking about which buildings are safest to operate as we're dealing with this crazy disease outbreak, here are some considerations for buildings that are maybe more safe and buildings that maybe are not quite as safe. And then, by the time we hit publish on that preprint, San Francisco closed down and Seattle closed down. And then it was stay-at-home orders basically across the country. And we rewrote it as if, okay, how are you going to operate critical infrastructure and how are you going to start to evaluate buildings that might be safer to reopen? And what mitigation strategies could we imagine start layering in this layered risk reduction concept to make spaces safer? And so, masks and increasing outside air, whether that's through mechanical ventilation systems or windows, increasing the outside air exchange rate or the air change rate total, adding enhanced filtration, maybe even thinking about disinfection strategies, the sunlight as a disinfection strategy. Anyway, so that paper was put out into the world and it was pretty quick, and it was largely based upon our confidence of having studied other pathogens in buildings. We have been studying Pseudomonas aeruginosa and Clostridioides difficile. My kid's school has had norovirus outbreaks, and we had done some investigation to try to figure all of that out. So we were able to pretty quickly put this together. We had similarly been, talking about aerosol transmission, and maybe some of you had seen, I don't know what it's going to take to make that play. Hopefully it plays. And maybe you had seen this, this visualization of the Guangzhou China restaurant. I'm showing it for a couple of reasons. One is because I think really the general public didn't kind of believe or have a conception of how aerosols move around a space and how viral particles could be caught up in those aerosols. So it is based upon our previous sampling of microbes in buildings that we were able to put something like this together. And then, well, what could operating a window and increasing outside air through natural ventilation do? And what could it do to mitigate risk? And so I think the other thing is that it introduced this idea that it's probably impossible to get to zero risk. And we need to start to conceive of, well, what level of risk are we comfortable with? And that's a hard one, right? Because especially early in the pandemic, but I would say even now, there's this expectation that, look, unless it's zero risk, I'm not going back to the office. Unless it's zero risk, we shouldn't be, opening schools or whatever. But we know that, grocery stores have been occupied, hospitals have been occupied, long-term care centers have been occupied. And yes, there have been outbreaks, but it's not at every time. It's not in always. So how can we start to understand, well, what's a reasonable amount of risk? And I'll cue that up for more topic conversation in a bit. So we pivoted really quickly from talking about C. diff and MRSA and Pseudomonas aeruginosa or norovirus, and we pivoted to talking about SARS-CoV-2 or coronavirus. I just want to highlight Patrick and Leslie from the team who ended up doing a lot of the field work. Here you can see them up at the hospital, in the wet lab, sampling in air handling systems. So these folks are trained about half that crew is trained in microbiology and the other half is trained in engineering or architecture or whatnot. So it's a really interesting team of people to work with. And these are the tricks of our trade, this hybrid indoor microbiome work, surface swabs, glorified Q-tips, passive settling plates, otherwise known as Petri dishes, but we use them to catch dust that lands out of the air to land on them, and then active air pumps. So there's a little fundamental difference between the heavier particles that fall out of the air and land in a Petri dish versus the one that tends to stay in the air for hours. those sub 4 micron size particles or sub 3 micron size particles that may stay in the air and float around in air streams, or really even very still air for hours. So we sample all 3 of those different ways. We use a really similar protocol as to what, if you've by now, probably most of you have had a COVID test, one way, shape, or form. But it's a really similar protocol. It's just a different sample. So instead of sticking the swab up the nose, we're swabbing surfaces in a room, or grabbing active air samples. We're using this reverse transcription and the polymerase chain reaction, or qPCR, which is all the same exact stuff. WHO and CDC guidelines for those procedures. It's really the gold standard for testing, and we're using a similar approach. Now, there's a lot of argument about, well, this is sort of overkill for human testing. Maybe there are faster, easier lateral flow assays and whatnot that you can do for human testing. And I'm not going to argue that there may be more efficient ways to do human testing, but I will say for environmental testing, where you're dealing with at least an order of magnitude, if not multiples order of magnitude, more dilute samples than when you're sampling right in someone's mouth or nose, the highly specific and highly sensitive methods are super useful. We can say with a great deal of confidence that we know that we're measuring SARS-CoV-2, and we can measure down to just a few gene copies. So we started sampling in other places in the hospital, and then the OB doc said, hey, what about us? And the reason they said that is because they weren't getting access to the PPE yet. Anywhere from 1% to 15% of the moms, depending on the city and where we were in the surge of the various waves, of those moms were coming in with COVID, whether they were asymptomatic or symptomatic. Somewhere between up to 15% of the population at different periods of time were coming in COVID positive. And so the OB docs delivering babies saying, hey, these are aerosol generating procedures. Let's study this. And so we took those tools and we took them to operating rooms with 20 air changes per hour, where they were doing C-sections, or patient rooms at 6 air changes per hour, where they were delivering vaginally. And we did sampling. This is an operating room. You see the red is the supply air, the blue is the exhaust air, empty black spots are surface swabs that came back negative, no SARS-CoV-2. Red dots are settling plates that came back negative, empty dots. So we tested before the procedure, and everything's clean. We also have an active air pump there, 2-3 meters away from the person, to check for aerosols, and everything comes back negative. That's the story you want to hear. It wasn't always the case, I will say. And then after the procedure with a COVID positive mom, we see there's a settling plate and an active air pump that turns positive. Now, a lot of those surfaces remained clean, pretty amazing. That's a lot of air change, and it's a room that's designed to minimize infection, right? And it's a highly controlled environment. Now compare that to an operating room a labor and delivery room where there's a different set of activities going on. And you can see we had a whole different story, right? We have a lot of swabs and a lot of petri dishes testing positive sprinkled around this room, many, many feet away, as you can see. Now, the laboring mom, was probably moving around, just wasn't stationary in the bed the whole time. We had an active air pump here that collected 3 times as much aerosol concentration of the virus as the room here. Here we had 5 gene copies per liter of air, or 500 gene copies per cubic meter of air. And here we had 15 gene copies per liter, or 1,500 gene copies per cubic meter of air. Interesting, roughly 3 times as much ventilation rate also in those 2 rooms. Heavier breathing, of course, and more shouting probably in the labor and delivery room. But also interesting was that the exhaust air, or the return air from the room, tested positive. And we also saw it on the floor outside the hallway. So this led us to ask the next question, which is, well, what about air handlers? And so this is still a preprint. Eventually, it'll get through peer review. It's been sitting in peer review for, 6 months. So it's still a preprint. But we went up the air handler, and we started looking at the different floors of the building, what air handlers are supply and return air from those floors. this was done actually during a period of time where there was a lot of outside air because it was pretty mild, if you will. The building was able to operate in economizer mode here in Portland, Oregon, during most of this sampling, but we were still able to sample and detect SARS-CoV-2 at multiple locations within these room-sized air handlers. So there's Leslie sampling in one of them. And you can just imagine Leslie standing in here sampling. There was the MERV 10 pre-filter, the MERV 15 final filter, and then just after the final filter, there's a series of regulating dampers because this is a big hospital. Multiple air handlers are ganged up and they modulate how much air total is delivered by modulating how much is coming from each air handler. But it gave us another point of impaction shortly after the final filter before the air is delivered into the various rooms. And we've sampled multiple locations from multiple air handlers, 3 locations from 3 air handlers. And in every air handler, every single location had some positives. Not every single swab that we took was a positive, but every location had some positives for the presence of the virus. Now, the big question, and we got a lot of positive and negative publicity around this preprint, because MERV 15 is higher than ASHRAE is recommending MERV 13, and we're showing that, well, look, some virus might make it through. So we were very, very careful to say that we don't know that the virus particles that we sampled, or the RNA even that we sampled and tested positive, suggests that it's a valid and viable virus or that it's infectious. That takes a whole separate set of assays, more expense, more complication. We are continuing to go down that road, but I don't have results I can share today with you on that. But it did raise the question of, well, do we need to think about that potential for aerosol transmission through HVAC? Now, it's a pretty tortured path, but the air does move pretty quickly. It goes from zone through air handler, and if it didn't get exhausted, if it was recirculated, it goes back to zone within anywhere from 2 to 6 minutes, depending on where in the hospital we're talking about. So from a conceptual viability, it could absolutely still be viable for that period of time. The question is, can it be viable through a tortured path, through a filter bank and whatnot? Okay, so where are we headed? We're trying to then make the bridge or bridge the gap between sort of a fear-based approach to building mitigation and an evidence-based approach to building mitigation. So, and we're also trying to manage this in the context of, 2 pandemics or 2 epidemic, or sorry, let me get the words right, crises. The global pandemic and COVID, and global climate change and the climate crisis. So we have to figure out the both and. We have to figure out a way to operate buildings that support human health while also managing energy. And as you know, probably because we've all been paying a lot of attention to this, a lot of the recommended practices just increase energy consumption. In particular, increasing outside air, either percentages or total air exchange rate with more outside air, you can really increase fan energy and specifically heating and cooling energy associated with that. There's even some people calling into question the validity and concerns around, viral transfer through heat exchangers. And I'm not going to get into that, but let's just say energy efficiency is under attack. But we have to figure out both together. And what I think is exciting about that is it forces us to be more creative, and we're all designers in one way, shape, or form. We all care about energy and high performance buildings, or we wouldn't be at an IBPSA event. So let's take this bigger problem and see if we can solve both problems together with innovation and maybe even come out better off for it. Can we get both and? Can we get healthier buildings that are also more energy efficient? I absolutely believe we can. So the other piece about this is we're all living, in these little virtual bubbles. And, there's been a lot of, well, don't, stay 6 feet away, don't touch me. And while I think there's some validity there, because absolutely, there's evidence of contact-based transmission, I think, in my belief, spent too much energy thinking about surface transmission and cleaning and disinfecting, and not enough time thinking about air. And the other piece about this is we have to find a way to be human with one another. Like, I miss not congregating together indoors. I run a lab, and you saw the team. It's hard to run that. It's hard to run the team. It's hard to build team, especially new team members that we bring in that aren't familiar with interpersonal dynamics and don't know one another. It's so hard to learn. It's hard to meet one another and get to onboard a new team member virtually. And that's just going to keep getting harder. I've seen it when I, teaching last spring, when I knew a bunch of the students, versus teaching in fall when there's a whole bunch of new faces. This is going to get harder. And I will argue, as we start to sort of move away from 100% virtual environments back to these hybrid environments where I'm teaching some students virtually, or we're having some meetings virtually, but other people are in the room, I'm going to be less likely to be focusing on the computer, and I'm going to start focusing more on the people in the room. And that's going to be even one more level of separation to everybody who is not in the room in experiencing the meetings virtually. I think that's actually going to be harder from a teaching or from operating a business, a design firm, an engineering firm, whatever. When we have to start doing that hybrid as opposed to basically 100% virtual, it's going to get more challenging. But ultimately, we need to find a way to be together. And buildings are where we do that. So the recast or the reframing I hope that this talk brings to everybody's minds is that, on one hand, we need to get the pathogens out of our buildings, and we need to find a way to do it as energy efficiently as possible. And my attitude about the way to stitch that together or thread the needle is by looking for the both and really, I'm going to argue, support broad human immune function and look for strategies that support broad human immune function. And that could be daylight. Daylight's my favorite thing. If you know me, if you've known me for a while, you know that I love daylighting. It's what I got passionate about. It's why I ended up doing maybe building science stuff as opposed to design. Was I loved working with architects and engineers on doing better daylit buildings. And I think it's probably many reasons why I got passionate about it. But from anecdotal to everybody wants the corner office with views and daylight, to the sort of mathematical equations that we can run and show that you get better daylight, or better daylight leads to improved circadian entrainment, which leads to better sleep, which leads to better weight management and better mood. So there's this really better daylight is a more beautiful building. Pick your favorite architect, and they've got amazing quotes around daylight as the form giver of architecture or whatnot. So but so it's beautiful. It can save energy. It can support human health, and it can even minimize the presence of unwanted bacteria and viruses indoors, which I think is pretty cool. All right, so daylight, indoor air quality, and controls. Like healthy buildings, energy efficiency. It's 1, 2, 3. It's daylight, indoor air quality, and control. It's too simple, but it's okay. We can bundle some things together. So first, daylight. I mentioned this. There's historically 100 years ago, there was evidence that daylight and light had a bactericidal effect. We have modern genomic technologies, like I described at the beginning of this presentation, that allow us to test that now with new techniques. So culture-based work is one way to approach it, and then also this next generation DNA sequencing or RNA sequencing or metagenomics, a lot of different techniques that can help us understand what is the microbial viability. And these graphs are really basic little daylight dollhouses, as our biology friends call them, but they're just daylight models. They're made out of stainless steel and hermetically sealed. and then we put different microbes inside of them, and we look at what different glass types do to the indoor microbial community structure. And really simply, you can see that with more daylight, there's I'll let the host unmute. Was I on mute?
Just
Okay.
briefly, sorry.
Okay, no worries. So you can see the inverse relationship. The more light, the less microbial survival. And then we've done a lot more work, and there was a paper published in 2018. Some of you maybe seen me present on it. I'm not going to redo it here, but we see fundamental shifts in the bacterial community structure with different amounts of light and with the absence of light in darkness. And we can start to actually see that perhaps there are fewer pathogens or unwanted microbes in spaces with better lighting. So that's, I think, pretty exciting and supports this idea of like, let's find strategies that are not just like attacking the bad microbes, but are also more holistically supportive of human health. And I think that's a big piece of our pathway forward. I think daylighting is a core of it. So I have to give a plug to some students who are launching this product here soon. This was born out of mostly 2 decades of pulling my hair out related to trying to create daylit spaces that were absent of glare. It's really hard. And I've been on record saying, actually, I don't know that you can create a really well daylit space that doesn't have some glare sometimes. Challenge me on it. I'll take it. And so this idea was, well, let's embrace the glare. 90% of respondents say if they could have sun in their space, but not in their face, they would love to have sun. But the challenge of open office environments is that sun in the space for some person is in the face for someone else. And so this whole idea was, how can we get the view? How can we get the sun? How can we save the energy? And how can we keep the blinds open as often as possible? So it's like basically personal shading systems. So that's that. And I use it as just a thought piece. It's cool, I think, and you can support the students if they launch their Kickstarter campaign and whatever. But I also think it's kind of emblematic of what I hope we'll all strive for, which is, let's think of products and technologies and solutions that we hadn't thought of before that solve multiple problems at once. All right, indoor air quality. So I've talked a bit about microbes in buildings already. This is from about a decade ago, and we were looking at bacterial community structures, not viruses, but there are some corollaries that we can draw here. And we looked at this business complex, and we looked at offices, and this is a lobe plot of the different bacterial clades. And you can see, if we zoom in really quickly, that each office has an abundance of certain types of bacteria and a dearth of others, and that's a different signature than restrooms, and it's a different signature than classrooms, and that may be because of the activity, the materials, the presence of water, what you do in bathrooms different than what you do in offices. And we saw that air handlers associated with these spaces also had different signatures. This was my clue to let's go chase COVID and air handlers. And we can see that offices that are closer to one another have different signatures than offices that are further away from one another. And we started to look at airflow patterns, and we noticed that offices that were mechanically ventilated, or classrooms that were mechanically ventilated, have a different signature than classrooms that were naturally ventilated. It's the same outside air, but it's getting filtered in one and it's getting recirculated in one. And then in the other, it's more abundant because it's night flush cooling. You're getting 20 air changes per hour, as opposed to with a mechanical ventilation system where you're maybe getting 2 or 4 air changes per hour. And then you look into the actual community structure and you see, wow, there are actually fewer human-associated bacteria in the spaces that are more abundantly naturally ventilated. And maybe that's about the solution to pollution is dilution, or maybe it's about seeding the indoor microbiome with more abundant, unfiltered outdoor microbes. And that actually creates sort of a Darwinian competition associated with the food in that space. And you don't create an environment where a nasty microbe can take hold and grow. Now, let's be clear, with COVID, we're not talking about microbes collecting on surfaces and growing so much as we're talking about time spent in a shared airspace and breathing other people's exhausted air. But the way that this does come together is, well, that shared airspace will have more particles containing viable virions when you have lower airflow. And so there are some overlaps. In a naturally ventilated space, chances are has higher airflow rates, not always, and it's more variable and less controlled. So, I get it. And believe me, a lot of engineers, I've had the arguments with lots of engineers about, well, there's a chance that the microbe's going to fly out one window and swim in another. And guess what? You want to find a paper? There is papers out there that will show this is possible, especially for SARS-1. But I would argue, on the balance, natural ventilation is a strategy that we should really be thinking about, because people like it. It supports human health more broadly, exposure to more diverse microbial community structures. It can reduce energy if we do it well. It makes the space more pleasant, connects people with nature. Chances are, if you have natural ventilation, you've got daylight, So, okay. So, well, what about controlled systems? Maybe there are some mechanical systems that we can really be thinking about to find the both and, and notwithstanding some concerns around viral transfer through certain types of heat exchangers, I would still argue probably pretty minimal. The viral transfer from a heat exchanger compared to the viral transfer from a recirculated air is orders of magnitude different, right? So unless you're in a 100% outside air scenario, it's hard to argue that the heat exchanger transfer is going to be the cause of concern as compared to the recirculated transfer that most buildings experience. So there are a lot of different heat exchanger strategies. What I like about this one is it's conceived as a retrofit solution. There are two or three manufacturers in the that make these really high efficient systems. The one I'm showing is from a company called Ventacity. It's a relatively small company here in the Northwest, but they're paired up with Fujitsu. And what I like about it is it also pairs the idea of heat recovery ventilation with distributed ventilation. What I think is intriguing about distributed ventilation is, when we're dealing with large central systems, there's just a greater likelihood that you're going to be mixing air between spaces that may have had a COVID positive individual in it. Now, there's a huge dilution profile associated with any of that recirculated air. And by now, a year in, I think if this was a major concern for outbreaks, we would have heard about more stories about it. But I will say there's some unknown here. And we can't be 100% certain that there hasn't been HVAC transmitted infection cases, because it's so complicated and hard to pull apart. Was it the HVAC transmission, or was it someone in a room at the same time? And it's really impossible to pull these things apart. So I do like the idea of distributed ventilation. Here's really simple concept of window-based ventilation. Talked about natural ventilation, and then here's a couple manufacturers that actually make little micro heat exchangers that are distributed in the window unit itself as part of the frame of an IGU. So I think the notion of creating smaller airspaces, smaller shared airspaces, is something that we could be thinking about. And to the extent that that supports better ventilation for the zones that need it versus the zones that are basically empty, I think it's really intriguing. All right, converging crises. We're also dealing with wildfire smoke here in the Oregon. We had to shut down because of COVID. We had to shut down because of wildfire. I built my first homemade filter fan, taking the box and grabbing some MERV 11 or MERV 13 filters from Home Depot and taping the box fan and trying to find solutions that we could, because I couldn't buy HEPA between COVID and wildfire smoke. I couldn't buy HEPA for the house. Eventually they came about 2 months later. But find creative solutions for the both and I think this one's crazy, but maybe there's a pathway forward. This is a doctoral program, a doctoral student piece of research that we're working on. And, this is what academics are for, is to try to think about some unusual ideas. This one is called a Zola, and it's really efficient at sucking CO2 and spitting oxygen. So that was part of it. But, it's also a humid environment, which dampens, grabs particles out of the air. There's some biophilia concepts here. And so, while I don't think any of we're not going to put a bunch of plants in our buildings to create clean air, maybe there are some ways. Then you pair that idea with like a micro breathing zone. Could you create smaller shared air spaces that have some amount of oxygen generation when you don't have safe air outside and you don't have safe air inside because of COVID? So those are the kind of things we're thinking about. I'm going to do a real quick litany here and then open it for questions. The controls piece will be brief, but we're trying to quantify this. So this is a free resource called safeairspaces.com. It's at safeairspaces.com. And it's trying to put some numbers to the risk profiles associated with different types of indoor spaces. So I'm just going to mention that and let you go look for it for yourself. I want to mention one other piece of research that we're working on, where we're actually looking at what are the surface inactivation effects associated with ultraviolet light. So far, we're conceiving of this as an open window where the full dose of outdoor illumination comes in like a stream of sun through an open window. And then we're going to layer in the UV filtering effects of glass and look at the results. But what's kind of cool, UVA and B on the left, UVB only on the right, minute by minute radiant simulations paired with the UV inactivation curves published for SARS-CoV-2 shows that it's not zero. So this is my connection back to simulation. So like, can we predict how fast with a certain daylighting strategy that we can inactivate any SARS-CoV-2 that might have landed on a surface? And you can see on an order of minutes, we can inactivate it with both UVA and UVB. And then likely over the course of a day, even with the UV filtering glass, that we can see some implications. So finally, control. How do we bring this to control? How do we make more use of data so that we can support healthy buildings operations? We all know there's a lot of data streams, data overload. We can't use them all. It takes a lot of work to try to use them all. And I am going to talk about adding data streams. But I think the idea here, the first thing I want to emphasize is we've been operating our buildings out of fear of an outbreak, and let's throw every strategy that we can at the building to try to make it safe. So we're increasing outside air, we're increasing air exchange rate, we're increasing filtration, we're buying technologies and duct blasting with ultraviolet irradiation. We're contemplating various ionization techniques, needlepoint, bipolar ionization, or whatever. We're doing huge amounts of surface disinfection. What else am I missing? I'm sure I'm missing strategies. We're not going into our buildings, even though we're doing all of that. So we're spending more on chemicals and on energy, and we're not going into our buildings anyway. But we haven't invested in a piece of data, in a process of collecting data that will help us know if any of that is working. Now, maybe we've started to contemplate CO2 monitoring as a proxy, or particulate monitoring as a proxy. And I think that's great. And absolutely, like, let's start layering those in. But I'll argue that right now we could add a data stream about the presence of the virus in our buildings. And there are a lot of companies out there that are doing it, that are providing that as a service. And we are doing it as a research team. So can we bring some evidence to guide building operation? Could we make choices about outside air, or about occupancy, about occupant density, about human contact tracing, as opposed to app-based human contact tracing, which they do in Korea, but we don't want to do here from a privacy perspective? Could we do spatial contact tracing and say that space had an exposure on June 29th at 2 p.m., And therefore, these are the people that were associated with that space. Those people may want to quarantine. Those people may want to get a test, whatever. Let's deploy enhanced filtration, even if it's just deployable HEPA filters in the rooms to those spaces. And let's target our solutions and our strategies based upon some evidence and some information. So that's the conception that we tried to put together here. It was a theory, and then we had the pleasure of collaborating with some folks to try it out in reality. We've heard a lot about outbreaks, and we think an outbreak is like the Guangzhou restaurant where they sit and have lunch for an hour and 15 minutes and 9 people get sick. And that happens. The South Korean restaurant where they had 5 minutes of overlap and there was an outbreak, that happens. But so do the slow burn outbreaks. And I think probably the slow burn outbreaks are the ones that you don't hear as much about because they don't become so pointed and evident that it was a specific event that resulted in an outbreak. So we see this slow burn outbreak like the South Korea call center from early in March. And they did their contact tracing, and we learned that, look, before they shut the building down on March 9th, there was about 3 weeks of time where there were people in that building that had the virus. And what I'm just trying to argue here is we could get a head start, perhaps with a viral monitoring program right now that does a 24-hour turnaround before you get the results. But in the future, could be real time. And we're actually working with some companies that are building real time types of technologies. Perhaps you could get even faster and prevent these outbreaks from happening and detect one person by sampling the HVAC return air or exhaust air. I don't think it'll be perfect. I don't think this is about getting to zero risk, but I do think it's about finding a way to occupy buildings again. The company that I mentioned at the very beginning has done this work in hundreds of long-term care facilities over the last several months. This was a pilot study that I'm showing some data from, and they showed that they were able to detect it in the environment a week before the person presented with symptoms. Now they're testing people once a week, but they're testing spaces once a week. You can't test every person every day, but you could potentially test every building every day. So they found a head start, that this environmental surveillance gives them a head start. Okay, so with all of that said, I just wanted to say I think the future of healthy buildings is a combination of daylight, improved indoor air quality, and bringing data to it and integrating data together through smart controls. So with that, I'll pause and go to questions.
All right. Well, thank you, Kevin. This has been a very interesting and informative talk. I want to give everybody a moment to put their questions into the chat. While we're waiting for some of those questions to come in, I have one of my own. A lot of the things that we've looked at, seem like they're kind of hard to quantify. And I think people have seen a lot of products advertised already where there's might be some question about how effective they really are, or how the building that they're put into will affect their effectiveness. Do you think that there's some sort of a rating system or some way that we can consistently measure the efficacy of different means of making spaces safer and healthier so that we can compare those different products and approaches to building safety?
Yeah, and I think some of what I showed there, these genomic-based approaches can be part of that in the future. There are a lot of layers to that onion, if you will, and I could go really quickly through them. Like the first thing you could do is look at CO2 and say, look, if your ventilation system is managing your CO2 to something near ambient, you're moving in the right direction. The next would be particle counts. Can you get a PM 2.5 or a PM 10 or even better, 0 to 10 resolved particle counter into some of your spaces or your air handling systems. And I think with data over time, we can learn more about how you can use that to guide operations. The next would be these 24-hour turnaround, RNA tests like I showed you today. The next would be more advanced genomic tests about which strain is it. The E117 strain out of the UK shows to be more transmissive than other strains. So maybe we would operate our buildings differently if E117 was there. Well, that means you have to not just collect and detect, you have to collect, detect, and then sequence to learn which strain you have. And then the next question is, well, is it really viable? And so then you collect, detect, test for viability, which is a culture-based assay for the most part, though we're looking for lower cost ways to do it. So, but there's the layers of the onion, and we can decide which layer is the most appropriate based upon which question. And truly, chances are most of that is going to have to be kind of laboratory-based work to get all the way to the core where you're indeed testing for infectiousness or viability of the pathogen. But then as we get better at that through laboratory environments, how can we create proxies for the real world environments, and make it faster, cheaper, easier, and something we can actually operationalize?
All right, thank you. We have a question coming from Eric. Eric, do you want to ask your question?
Sure, thanks, Nathaniel. Yeah, Eric Holderup here, and thank you, Kevin. I was wondering about glazing selection and whether there's enough known to provide guidance on, glazing selection to optimize impact on microbes indoors. Are different types of spectrally selective coatings recommended over others?
Yeah, it's a great question. Unfortunately, I don't have much to share with you on it. There's just so little research that has been done. I think the big takeaway is probably more than worrying too much about enriching. There's a reason we don't put UV light into our buildings. It damages goods, it erodes colors, and so I think it's less likely. I would imagine in the future we're not going to be necessarily enriching UV light into our buildings from the outdoors, UVA and UVB, but rather just understanding that daylight, whatever the wavelength, that daylight does make a difference, and sort of the intensity. This is I think it'll be a similar conversation, and I have a little bit of preliminary evidence to suggest that I'm not just making stuff up here. It'll be a similar conversation to the circadian dose cares less about spectrum and more about intensity. I think likely the viral or bacterial survival rate is going to care more about dose and less about spectrum.
Okay, thanks.
Got a question coming from our YouTube live stream. What's your take on the fact that US minimum ventilation rates in ASHRAE 62.1 are rather lower than some other parts of the world? Do we need to rethink the minimum requirements we design buildings to?
I think the short answer is yes. The trick, the devil's in the details, and how do we manage both of these crises at once? Because bottom line is you increase outside air exchange and you can do things to make it less bad in terms of you're going to use more energy. You can make it less bad, but you're still going to use more energy most of the time. So I think it's so important to figure out I've been thinking a lot about risk on, risk off. Like, can we figure out a way to get our buildings and our operational protocols set up for a risk on, risk off scenario? And what can we use from a data stream perspective to help guide the risk on, risk off scenario? There's a lot of things, right? You could actually imagine systems that integrate with community health data. What's the positive test rate for influenza? What's the positive test rate for SARS-CoV-2? That could actually dictate building operations. I think we're still talking about a future, because right now, basically, it's like, yeah, we're just all at home still, with the exception of a handful of places like long-term care and hospitals, and manufacturing facilities. But I think those are the places that are going to contemplate this first. And we're working with the public health authority to try to revamp HVAC guidelines for long-term care, and at the same time we're trying to revamp it from a design standard. We're trying to help them figure out cost-effective ways to mitigate or enhance, like low-cost retrofits. So I think that's going to be a big chunk of work over the next several years, and standards take a long time to change. I think ASHRAE did a great job getting standards, recommended practices out quickly for the COVID pandemic, but to really codify them and, into formal standards is going to take time.
Got a question coming from Abdel. Abdel, would you like to ask your question?
Yes, I would like, but before I that, I just want to mention, I'm a member of the 62.1 committee, so and I totally understand how much time it takes to codify these things, and it's always it's a challenge because 62.1 is not really focused on infection control. So when you try to bridge this between with actually 170, which is the healthcare, and then you get into this. Yes, is infectious important only in commercial building or only in hospitals, and where do you draw the line? So it's not an easy line to draw. So my question, doctor, is, well, first, it's a great presentation. Based on your field work, did you find any evidence of long-range airborne transmission of SARS-CoV-2, like TB, like for example in the OR and then the labor delivery room that you tested? Were there any infectious for other patients that did not see the COVID-19 case or did not come in contact with them or not in the same room? Did you see this or not?
Yeah, so it's a really, really good question, and the word choices are so important. And so I'm not a medical professional. I'm an architect by training, trying to figure out mechanical engineering and microbiology, which is what I spend most of my time doing. So I've talked with a lot of folks in infection control. I've talked with a lot of medical doctors. The trick there is it's really hard to say that so-and-so got sick because of this particular transfer mechanism. So I can just really quickly, short answer is saying, well, nope, I don't have proof and evidence of the exact question you're asking. My sense is we've spent enough time in these spaces. We've seen different aerosol concentrations at different air exchange rates. I've been in lots of COVID positive rooms. I've had team members in lots of COVID positive rooms. We wear our N95s. They've been fit tested. They work. We're not getting sick. So I'm absolutely convinced that managing air is incredibly important to this problem. But as far as saying, look, I have bulletproof evidence of something like long-term, long-range transmission, I don't have that in my data set.
Okay, thank you.
We have a question coming from Hiba. Hiba, would you like to ask your question?
Yes, thank you. Thank you, Nathaniel. And I want to thank you for this great presentation. I want to ask about the harsh climates, if it's very hot or very cold outside. So the cross ventilation is not recommended or not. We don't want it, and we want the cold, not the hot air. So do you have any like passive technique to make the air cold before entering the building, and weighing between the daylight and the thermal comfort, or making an equilibrium between the natural ventilation and the very harsh hot climate?
Mm-hmm. Really, really good question. So thank you. The thing that comes to mind is like we have low energy, net zero energy kind of strategies in our mind. We've all been working on them together for a couple of decades. And I think some of them can carry over here. We have to be careful, of course, of not ratcheting down fresh air so far, and probably look for ways to enhance it. And you mentioned cross ventilation. Well, the challenge with natural ventilation is, well, it's hot outside sometimes, or right now it's freezing here in Eugene. We can't just dump a bunch of outside air in through passive means. So how do we create thermal comfort and manage this increased outside air without just burning a bunch of fossil fuel or spending a bunch of energy in general? So my mind goes to some of those strategies that we've been using for net zero energy buildings. So like the separating of ventilation from heating and cooling, that's a sort of staple. The benefit of radiant fields, right? There's actually, back to the sort of broader human comfort or broader human health conversation, I think there's there's a lot of really interesting evidence around the benefit of radiant fields to support human health, not just human comfort. And that's really intriguing because you can actually afford more fresh air, even if it's a little chilly, when you have radiant fields. So can you use those kind of strategies to overcome? And then, you know, maybe they're harder to implement in every common building type, but things like, you know, thermal storage, night ventilation of mass, earth tubes, transpired solar collectors, you know, ways that we can manage air and thermal environments in a more aggressive, you know, manner, I guess is what comes to mind.
All right, thanks. We've got a question coming in from Joyce Kelly on the live stream. When do you think we'll know whether sampling is detecting live or deactivated virus?
Yeah, great question. Couple of ideas on that. So this is not perfect, but I will say if you're doing an active air sample, chances are much higher, especially if you're getting a highly concentrated active air sample. When you do this work, there's a phrase called cycle threshold, CT. Maybe we've heard of CT values if we've been listening to virology kind of things in this COVID world we all live in now. So the lower the CT value, the higher the abundance. It has nothing directly to do with infectiousness or, you know, viability. But if you're seeing lower CT values in an air sample, I would say there's an increased likelihood that that's an original introduction. And if it's very low, it's perhaps an original introduction during a period of time when that person may be shedding a lot. And that these are a couple of leaps that we have to make, but you could say that it's more of a risk than a lower concentration in the air that maybe could have happened from resuspension of dust, or maybe a low positive surface sample. But I would say you can look at that CT value, which we can get really quick right now, to give you an estimate of concentration, and that can be a bit of a proxy for infectivity. It's not a perfect proxy. And then to the really directly answer your question, I mean, the turnaround time for assays that truly determine viability are not of a scale that would be operationalized in a building. You could use them to confirm a technology in a building, or confirm a technology in a wet lab. But in terms of operationalizing it, you know, it just takes a day for the culture to grow at a minimum. And some cultures take days to grow to verify infectivity at all, and what proportion is infective, or what they call the TCID 50, what portion, you know, of the population is infected. So I don't see that quickly operationalizing in buildings from a controls standpoint, though I think there's plenty of pathways to it to verify technologies that you might use in buildings. The only other thing I'll say is we're working on an assay that would be a proxy for viability that's as fast as the CT value, just the quantification assay. And if it works, you could get the viability results within 24 hours as well. So stay tuned.
Okay. We've gotten a couple of similar questions, so I'm going to combine them. Asking about the software that you used. So what software did you use for your IAQ visualizations with very nice 3D visualizations? Oh. And what other analysis tools did you use?
Well, so a lot of the visualizations you saw today, the videos, I don't know. It's a big team. I don't remember what software we used. The ones at the beginning were contracted out 10 years ago, and I absolutely don't know. The ones that we did more recently, I know we used a lot of Blender. And so you're going to see that is me painting microbes the way I want them to fly. I'm using magic arrows, but it's based upon previous CFD models. We've done a lot of work in TAS and COMSOL. So if you're if you're familiar with either of those, that's some of what we've done for building CFD.
All right. Well, thank you, Kevin. This has been a really great talk. I think it's been really informative. And thanks to everyone for joining this IBPSA-USA Research Committee webinar. One final reminder that AIA credit is available for attending today's lecture. Please email AIAEB or info@aiaeb.org. And please join us again on February 25th at noon Pacific time when Terry Peters presents A Room with a View, Simulating Daylight and Outdoor Space in Multi-Unit Residential Buildings with Balconies.